Hi everyone, I am Alessandro Conti and today we present the work on large multimodal models as open-world image classifiers. Traditionally, image classification has always been done in the closed-world setting, with the objective of selecting your answer from a list of predefined labels. And this is true for both traditional image classification approaches, so single encoder architectures, but also for dual encoder architectures, so more recent approaches which consist of using, for instance, clip to solve the problem of image classification, where for both approaches we have a strict need for a list of labels. On the other hand, we can instead identify open-world image classification as the case where we don't want to select a label from a list of candidates, but instead we want to directly generate the response from the latents of a model. And for this, we can identify large language models as good candidates to solve the task. Indeed, these models formulate the task of classification as a purely generative problem, removing any need for a classifier, but also making the need for labels completely optional. Then it's clear that large multimodal models can classify in open world, but how do they perform? And also, how can we evaluate them? We first respond to the second question and propose two properties we want to quantify. First is semantic relevance and second is linguistic inclusion, with the first one that roughly responds to the question of if the predictions are semantically close to the ground truth, and the second one responding to the question of if these predictions actually match the ground truth label. For semantic relevance, we propose two metrics. The first one quantifies the labels to sentence similarity, while the second one works on the parts of the response and quantifies the labels to concept similarity. Instead, for linguistic inclusion, we evaluate textual inclusion, so if the label is contained inside of the prediction, and second one is llama inclusion, so we ask a language model to state whether or not the prediction describes or contains the ground truth label. From the model side, we consider 7 open source families with a total of 13 different model instances, having different encoders and considering different training strategies. Here are the results on the 4 metrics we consider for the 13 models, plus some baselines based on clip extended for open world classification, where you can see that all of the models roughly perform similarly and all of them are more or less on par with the clip baselines extended for open world, so the red bars, except for cases where, for instance, in llama inclusion, some models outperforms these baselines. Notably, you can see that for all of the metrics and all of the models, there is a consistent gap between the clip applied in the closed world and these models applied in the open world, underlying the fact that we still have some margin to close. If we combine the metrics we have defined, we can also categorize the model's behaviors into different groups. First of all, we can see that relevance directly predicts whether or not a generation is specific or generic, while inclusion, on the other hand, tells us whether or not a prediction is correct or wrong. By combining these two properties, we can actually identify 4 model behaviors. The first one is correct and specific, so situations where the model directly predicts the exact ground truth label, so pug against pug dog, for instance. Second one is the case where instead the prediction is still correct, but it's maybe slightly less specific, so maybe we say dog instead of pug. Third case instead consists of cases where we actually misclassify a image or an object for another one, so the case where maybe we say Labrador instead of saying it's a pug. Last case instead identify the situations where a model completely misclassifies the content of the image, so maybe it says there is grass instead of saying there is a dog. And you can see this behavior from a sample point of view, where we highlight by the length of the bar the similarity of the prediction to the ground truth, and also by the color whether or not llama states the prediction is correct or wrong, where red is wrong and blue is correct. Where, for instance, in the first case, you can see that creamy sauce has an higher similarity to caprese salad, but it's considered wrong by llama. Instead, food, it's more generic, but it's considered correct. You can see a similar behavior when you actually visualize in a two-dimensional space the predictions of models for a specific class, where you can identify 4 subregions in this space, where on the x-axis we have the average llama inclusion and on the y-axis we have the average concept similarity. Indeed, on the left part you can see wrong predictions, and on the right part we can see correct predictions, with the top part being more specific and the bottom part being more generic. And you can see that there are situations where we predict the exact same label in the top right, or we misclassify for something else on the top left part. Then we also explore how we can control this behavior, so if we can flip the generic predictions into more specific ones, and also if we can flip misclassification cases into correct cases. We also explore what are the completely wrong predictions of these models, and then scale our studies to larger and commercial models. We don't have time to cover everything in this presentation, so please, if you're interested in our work, come check out our poster, and you can also find our paper in the QR code below. Thank you for your attention.